Okay. So last week we introduced the chapter 7, and so today we will continue this chapter. So here I want to spend a couple minutes to review what we learned last time. So first we introduced the valence shell electron pair repulsion model. So basically we can use this model to determine the geometry of the molecules. For example, we know for this class AB2, so this is linear geometry. It's like this. And for AB3, so there are two geometries. One is about the arrangement of electron pairs, okay, and then the molecular geometry. For these molecules, they don't have no pairs, so basically they are arrangement of electron pairs. It's also the molecular geometry, right? Like AB4, so basically the arrangement of electron pairs is tetrahedral, and so its molecular geometry is also tetrahedral. So this is about the molecular without no pairs. But when they have, many molecules have no pairs. So in these cases, we can still the first step is to think out its arrangement of electron pairs. Now in this case, AB2E, so its arrangement of electron pairs is trichoplanar, but the molecular geometry is only this part, so it's band, okay. So here in this class AB4E, so its arrangement of electron pairs is trichobiparticle. So here the no pair electrons, these two no pair electrons should be in this position, and we also explained why these two electrons should be at this position, not in here. So in their geometries, so the steric effect play a key role. Okay, so here we can see two kinds of molecules. One is without no pair. Another one has the no pair. So we also introduced how to predict the molecular geometries. So the first step is Lewis structure, and then we can count the number of lone pairs on the central atom and the number of atoms bonded to the central atom. When we think out its class, like this one is AB2E. B2, it means there are two atoms bonded to the sulfur. And the E 1e. 1e means it has one no pair. So we know AB2E is molecular geometry is batch. Okay, it's like this. So this example is AB4E. So 4 it means there are 4 atoms bonded to the sulfur. E1E, one no pair. Okay, so we can figure out its molecular geometry. After we know its molecular geometry, we can determine the molecular is polar or not. Is polar or not. So we know for a covalent bond, it may be dipole. It may has a dipole moment. So dipole moment we can use like mu equal q times the distance. So the q is the charge. Well, in this case, we know the fluorine has higher electron activity, so it can attract more electrons to its sides, to its side. So basically, it looks like it has some negative charge, and so the hydrogen has some positive charge. So the charge, like Q, times the distance between them. So we can. So this is means dipole moment. Dipole moment. So for polar covalent bond, it has dipole moment. And of course, in this molecule, it only has the HF bond, so it is polar molecule. It's polar molecule. So, well, after we know the geometry of the molecule, we can determine the molecule is polar or not. But in this case, we can say the HN bond has bond moment. The direction of the bond moment is from hydrogen to nitrogen, because nitrogen has higher electron activity than hydrogen, right? And for these no pair electrons, for the two electrons, so the direction should be from nitrogen to electron. Why? Because nitrogen is like it's nuclear, right? And so electron activity. So the moment for no pair electron should from the atom to the electron. So we can combine these 4 moments together to get the molecular moment. So it has the moment. So this molecule is polar. Is polar. In this case, we can say the bond moment, the direction of bond moment is from nitrogen to fluorine. Okay. So the directions of these 3 bonds are different from this direction. So this moment will offset some moments of these 3 bonds. So this molecule has the value of the resultant dipole is very small. This guy is much higher than this guy. The reason is in this molecule, the directions of all moments are same. We can say the same, right? But in this, this guy is different from these three ones. So this molecule has the low value of dipole. So we also introduced how to determine the polar of the molecule. For example, in this case, carbon oxygen has moment, but the geometry is linear. So these two moments will offset. So it's the molecule is no polar molecule. It's no polar molecule. Okay. And also in this case, the carbon fluoride bond has moment, but all the moments of these four bonds will offset. So the whole molecule is no polar. Okay. So when we determine the polar of the molecule, we need to know their geometry. It depends on their geometry. Okay. So in this geometry and also in this geometry, they are no polar. But in this geometry, this kind of geometry, they have polar. They are polar. Okay. So, and also this is another example. For this molecule, the geometry of this molecule is all four atoms are in the plane, and of course, the moments of these three bonds will also be offset each other. So this molecule is no polar. Okay. And in this case, so we can say carbon chloride has a moment, and hydrogen carbon has a moment, and the directions of the moments are like this, and the final moment, the direction of final moment is like this. So this molecule is polar. Okay. So here we introduced how to determine the geometry of molecules, and then according to their geometries, we can determine they are polar or not. Okay. And this table to show the dipole moments of the polar molecules. Here we can see these four atoms are in one group. So we know fluorine has high electronegativity. So its dipole moment is much higher than others. Okay. Okay, so that's all we learned last time. So now introduce the third part of this chapter, valence bond theory. It's also called hybridization theory. So we learned the Lewis theory. We know also how to use the Lewis theory to explain the bonds in hydrogen, in atoms, in molecules. basically the like overlap, the bonds are formed by overlap of electrons of the orbitals like hydrogen. We know hydrogen bond is formed by the overlap of two 1s orbitals or the electrons in these two orbitals. Like fluorine F2, FF bond is formed by the overlap of two 2p electrons, right? So this is about this will learned from the Lewis theory. So in this theory, we also can say it's valence bond theory. So the bonds are formed by sharing of electrons from overlapping atomic orbitals. For example, in this case, the atomic orbitals are two 1s orbitals. So these two hydrogen atoms, share two electrons from the 1s orbitals, right? We introduced this, right? And so just when these two atoms they are close each other, so they are orbitals overlap, or they share the electrons from the overlap orbitals, and then form the covalent bond. So it's like this, right? Okay. Now the question is, now we just know the orbitals are overlap, but how do the orbitals overlap? We want to know more details about the overlap. So here we introduce the valence bond theory. So using this theory, we can know more details about the overlap of orbitals. For example, in this molecule NH3, so there are one nitrogen atom. We know its electron configuration is 1s2, 2s2, 2p3. So these two 1s, 2s electrons, and there it has three 2p electrons, right? So these three electrons will be stayed like this. One is in one orbital. This is decided by Honda rule, right? Okay. So besides the nitrogen, it also has three hydrogen. Besides the nitrogen, it also has three hydrogen atoms, and it has three NH bonds. Okay, we know one hydrogen only has one 1s electron. So basically, how to overlap? So just one, for example, the blue one is from the hydrogen. So here can still include one electron. So one hydrogen electron will be filled in here. Okay, and another one, the third one, So when the electron of hydrogen are filled in like this, so this nitrogen and the hydrogen atoms share these electrons. So this is also about the Lewis theory. Now the question is, if the bonds form from overlap of 2p orbitals of nitrogen with the 1s orbital on each hydrogen atom, what would the molecular geometry of NH3 be? Think about this question. So if the orbitals are only overlapped from the p and s orbitals, so what is the molecular geometry? We can say, we know the 2p orbital is like this, right? So 1, 2, 3, this means x, y, z. The orbitals of the 2p is like this. And the angles between the px, py, pz, so what are the angles between the px, py, pz? What are the angles between the px, py, and pz? 118?
90.
Yes, 90.
Oh.
Because axis means the electron along the x-axis, right? Y along the y-axis, Z along the z-axis, of course. The angles between them will be 90, right? So if we use the 3p orbitals and overlap with p with s, so it's like s will be in here, right? Ys will be here. Ys from hydrogen will be here. Overlap, right? Overlap here. So this means what's the angle between H and H? If like this, one hydrogen here, one hydrogen here, one hydrogen here, 3 hydrogens, right? If like this, because they overlap. If like this overlap, what's the angle between the hydrogen and the nitrogen? $90, right? For example, one hydrogen here, one hydrogen here, one hydrogen here. So this is, for example, for this guy. So it's like this, Z, Y, X. So one hydrogen is here, one hydrogen is here, one hydrogen is here. This is nitrogen. So the H and H, what the angle? You will use 90, right? But it's correct or not? We know the NH, what are the angles in NH3? In fact, it's 107, right? It's like a tetrahedron. Still remember the geometry of NH2, NH3. NH3 is the arrangement of electrons is geometry. Why is geometry? It has 3 hydrogen and it's one lone pair. So it's tetrahedron. So tetrahedron and the angles is like 107. In fact, it's 107. But if from here we can see the angle should be 90. So this means this overlap is too simple, right? Too simple. If they are just overlap like this, so the angle will be 90. It's not correct. It's not correct. Okay. So we should use the hybridization theory to explain, to give us more details about the overlap of octets. So hybridization means the mixing of two or more atomic octets to form a new set of hybrid octets. So this is about the hybridization. So here we can see a new set of hybrid octets. So basically mixed at last two no equivalent atomic octets. For example, we can mix the S and P octets together. Okay. And the hybrid octets have very different shape from original atomic octets. This is first point. Second point, number of hybrid octets is equal to number of pure atomic octets used in this process. Third point, covalent bonds are formed by overlap of hybrid octets with atomic octets. Now we can see the overlap is from the hybrid octets, not only from the atomic octets. It's from the hybrid octets. And of course, the hybrid octets are from the atomic octets, right? So we can overlap of hybrid octets with atomic octets, with atomic octets from another atom, or overlap of hybrid octets with other hybrid octets. So this is about the hybridization theory. So here we can see how to get the hybrid octets. For example, here is the formation of sp3 hybrid octets. What does sp3 mean? sp3 means 1 s octet and 3 p octets mixed together. This means sp3. sp3 is also s1 p3. Okay, 1 we don't need have to write the 1. So just sp3. sp3 is 1 s octet and 3 p octets mixed together to form 4 sp3 hybrid octets. Why 4? Why is not 3? Why? sp3, there are 4 sp3. Number of hybrid octets is equal to the number of pure atomic octets. This is why there are 4 sp3, because it's from 1s, 3p, right? So total 4 octets. So when they mix together, they also still have form 4 hybrid octets. Okay, 4 sp3 hybrid octets. So here, this picture shows the process. 1 s octet, 1, 2, 3, 3p octets. So these 4 octets can mix together to form 1, 2, 3, 4. 4 sp3 hybrid octets. And after the mixing, the shape of the sp3 octets like this. Okay, so this is different from this guy, right? Yeah, in this dumbbell shape, but in this, so this side is larger than this side, Okay, so now we can see the how to form the hybrid octets. So basically and one point is should be noticed is that we should mix the at least to no equivalent. What's mean no equivalent? No equivalent means you can mix S and P because S and P are different, right? Are different octets. You can't mix it like P, no, you can't. Okay? Or you can't mix two S octet. You can mix the S, P, or P, D, right? And also, we know the number of hybrid octets is equal to the number of pure atomic octets. Okay, now we know how to form the hybrid octets. After we get the hybrid octets, now we can see the overlap between the hybrid octets and the atomic octets. We know this 1, 2, 3, 4, this 3 sp3 hybrid octets. If we mix them together, if we combine them together, they will be like this, right? 1, 2, 3, 4. So these 4 sp3 hybrid octets, they are shaped like this. Okay. So for now, the first step, we get 4 sp3 hybrid octets. So in these 4 hybrid octets, how many electrons? At first, it has 2 s, 1 p, 1 px, 1 py, 1 pz. So in total has 5 electrons, right? So 5 electrons. So 2 will be here. It means no pair, right? So 1 is here, 1 is here, 1 is here. Okay. So for example, 1 px, this is from px, this is from py, this is from pz. And so this hybrid octet can overlap with the atomic octet of hydrogen, to form the covalent bond. So using this way, we can see what the angle between the H hydrogen, nitrogen, hydrogen. So now the angle is 107. 107. So using the hybridization theory, we can know more details about the overlap between the octets. Okay, it's not just simply overlap P and S. No, it should form the hybrid octets firstly, and then overlap with another atom's orbital. Okay. So any question for this hybridization theory? Okay. So now For this covalent bond, these covalent bonds are formed by overlap of hybrid orbitals with atomic orbitals. So the hybrid orbitals is sp3, right? sp3 hybrid orbital. They are from the nitrogen. They are from the nitrogen. With atomic orbitals, these atomic orbitals, where are they from? Question. In this case, overlap of hybrid orbitals with atomic orbitals. We know hybrid orbitals are from nitrogen. Atomic orbitals from, yes, from hydrogen. Okay. The hydrogen is 1s. So the 1s is not hybrid orbital. Okay. It's atomic, it's just only atomic orbital. Okay, so in this case we can overlap the hybrid orbitals with atomic orbitals. Okay. Second, this is another sample about carbon. So in CH4, how to form the covalent bond in CH4? We know carbon is 1s2, 2s2, 2p2, right? It only has 2p orbitals. The first step, s and p orbitals mix together to form 1, 2, 3, 4 sp3 hybrid orbitals. So we know it has 2 s electron and 2 p electrons. So total it has 4 electrons. So 4 electrons will be, so each one 1, 2, 3, 4. Okay. And in these 4 hybrid orbitals, each one has 1 electron. Okay. So it looks like 1 s electron is moved to the p orbital. Okay. So there are 4 single electrons. So these 4 electrons, these 4 orbitals can overlap with the atomic orbitals from 4 hydrogen atoms, and then form the CH covalent bond. And of course, the structure is like or geometry is like this. And in this geometry, we know the angles between the hydrogen, carbon-hydrogen is 109.5. So these covalent bonds are formed by overlap of hybrid orbitals from carbon and with atomic orbitals from hydrogen. Okay? So just now we introduced sp3 hybrid orbitals. This means using 1 s orbital and 3p orbitals, we mix them together. Here is about sp2. sp2 is means using 1 s. How many p? 2p, yes. Okay, have a short break.